light. It's going to talk right away about how light behaves as a wave. So it's going to have crests and troughs and move like that. It's also going to move like a particle because it can travel through a vacuum. So we're going to say that it behaves like both of them. On the other side, they're going to talk about photons. Photons are these packets of light. How fast does light travel? Light's going to travel the speed of light, which is 3 times 10 to the 8th, or 3 with 8 zeros after it, meters per second. Sound is pretty fast, but sound is definitely not as fast as light. If sound is 340 meters per second, light is much, much faster. It's why you see lightning before you hear the thunder. And then we've got, where does light come from? The origins of light and color. Well, back to those photons again, those packets of light. Those photons come from electrons falling from high electron orbits to low orbits. These orbits are called energy levels. So we've known from first semester, these electrons in the outermost energy level are called valence electrons. So when one of these electrons moves an energy level, then you're going to produce light. And then the light that we can see is called visible light. So we go all the way from red, which is our lowest frequency light, longest wavelengths, all the way to violet, which would be our highest frequency light we can see, and then the shortest wavelengths. Once you go beyond violet, that'd be called ultraviolet light. We can't see it with our eyes, but we can use special lenses to see it. And then if you go up before red, that's infrared light. We can't actually see that unless we have some special lenses. We can see those heat signatures. And then we've got down at the bottom the electromagnetic spectrum. The lowest energy waves on the spectrum would be your radio waves, really long wavelengths there. Then microwaves, those wavelengths are getting a little bit quicker. Infrared, just barely below our visible light spectrum, so you can't actually see infrared. Then we can see all the visible light colors once you go beyond violet. Now we're in ultraviolet, even higher frequencies, X-rays. So these waves would look very close together, high frequency compared to the low frequency on this side. And then each one's got a little bit more about it. But over here on the other side, you'll start with photon. We learned from the other side that the photons are those packets of light, or packets of light we call photons. So E says a single particle or packet of light. There we go. 3 times 10 to the 8th meter per second. That's a pretty fast speed, and that is the speed of light. So we're looking for the speed of light. A says the fastest speed in the universe, the speed of light. There we go. A prism. A prism. An orbit of electrons, no. All light, visible and invisible, no. Used to separate white light into its colors, yes. If you send white light through a prism, you might get a rainbow shining on the ground or shining on something. But yes, a prism is going to be D. What is light? It's not going to be the all light, visible and invisible. That's going to be this electromagnetic spectrum. So C goes with the electromagnetic spectrum. What is light? Is light an orbit of electrons to move from low to high energy levels, or is light a wave that can travel through a vacuum? Yes, light is a wave that can travel through a vacuum. That leaves, what is energy level? Energy level is an orbit of electrons to move from low to high energy levels. That's how that light is produced. All right, and then moving across the top to the radio waves. Actually, let's go this way. Electromagnetic waves we feel as heat. We talked a little bit about this last chapter, but infrared light is typically going to be those heat waves that you feel. Dangerous EM waves that have very high energy and come from nuclear reactions. Well, if they're very high energy, it's either going to be X-rays or gamma rays. Then it says it comes from nuclear reactions, and here we go for gamma rays emitted by nuclear reactions. So B is going to be gamma rays. C says electromagnetic waves that have very low energy and long wavelengths. So this one could be radio waves or microwaves. Both are very low energy. And it doesn't really tell us much. Let's skip that one and come back to it. EM waves that can push or can pass through the skin and have short wavelengths. Well, if they're passing through your skin, they're going to be X-rays. And they got short wavelengths as well, so they're going to be over on this side. We already used gamma rays, X-rays, wavelengths, pretty short, yes. Used in medical industry. And yes, you guys maybe had an X-ray before. You can see through your skin or the soft tissue, so you can check out if your bones are fractured or not. Or you can check other things as well. But we've got... E says electromagnetic waves with more energy than visible light and can cause sunburns. Some of you are familiar with those. These would be your ultraviolet light, UV light. You can protect yourself with some sunscreen to block or reflect some of that UV light. And then microwaves. This last one says long wavelengths used in cell phones. So let's see, are microwaves longer or are radio waves longer? Well, radio waves would be longer. Are radio waves used in cell phones? Well, they transmit radio and television signals. Wavelengths range from hundreds of meters to less than a centimeter. Microwaves used to cook food and by cell phones. So there's our microwaves. Microwaves are used for cell phone reception. So down here, cell phones matches up with microwaves. And that leaves us with electromagnetic waves with very low energy and long wavelengths. And yes, those would be your radio waves. Awesome. Then right here is light a wave or a particle? Prove your answer. Hint, look at the top right of the front page. Top right. Okay, let's take a peek. Oh yeah, we were here earlier. It says light is both. Well, over here it tells you why it's a wave. Light is refracted in lenses. Light diffracting around 2 fingers causes lines of darkness, destructive interference. So light must be a wave. And then how does light prove that it's a particle? Well, light can travel through a vacuum of space, but waves can't travel in a vacuum. So light must be a particle. This contradiction perplexed scientists for many, many years, but the evidence must be believed. Light is both a wave and a particle. So it is both. Prove your answer. Well, like it says over here, light moves like a wave. Light moves like a wave. And then why is it a particle? Well, it can also travel through a vacuum. Or we can say light travels through space. The only way it could do that is if it behaved like a particle. All right, put these 3 in order from slowest to fastest. Well, you have light, sound, and water. Our slowest would be the water waves. Next up would be sound. And the fastest would be light. Put these from shortest to longest wavelength. Well, the shortest wavelengths would be right over here, short wavelengths. So if we got gamma rays and X-rays, those for sure are the shortest. Do we have gamma rays? No, but we do have X-rays, so those would be the shortest of the bunch. Okay, then next up would come ultraviolet, then visible, then infrared. So ultraviolet, then visible, infrared if we had it, but we don't have infrared. The next one would be microwaves, and lastly, radio waves. So microwaves and then radio waves. All right, and then let's do the opposite. Put these in order from least energy to most energy. Well, our least energy of the bunch, low energy, is the radio waves. Radio. Then next up, microwaves. Then you got your visible light in the middle. After that, UV is increasing in energy, and then our highest energy wave of this bunch is the X-ray, or X-rays. All right, Where does light come from? Hint, look at the origins of light and color on the front page. All right, so right here, it says photons, aka light, comes from electrons falling from high electron orbits to low orbits. These orbits are called energy levels. All right, and so our answer here is photons come from electrons, or light comes from electrons falling from high electron orbits to low electron orbits. Falling from high orbits to low orbits. Awesome. And why do we see lightning and hear thunder a few seconds later? Well, what travels faster? Light is much faster. Okay, now let's go to this one. Find the period of a 10 hertz wave. Hint, find the inverse. Well, if you know the relationship between period and frequency, they're inverses of one another. So if your frequency is 10, that means your time period would be 1/10 seconds, or 0.1 seconds. Okay, and then a wave has these characteristics. 25 hertz as our frequency, 8 meters as our wavelength. Find speed. Our speed formula is frequency multiplied by wavelength. So 25 hertz multiplied by 8 meters. That's going to give you a speed in meters per second. A change from 25 to 5 decibels. How do we hear that change? Well, anytime you go down by 10 decibels, that is half as loud. So if you went from 25 to 5, you're going down by 20. So it's not half as loud, it'd be a fourth as loud, or 4 times quieter. So you can say a fourth as loud, or 4 times quieter. Okay. You hear thunder 3 seconds after you see the lightning. How far away is the storm? All right, well, we got to know how fast sound is going to move every second. Well, sound goes about 340 meters every second. You could say 343 if you want, but about 340 meters in 1 second. So how far would it go after 3 seconds? We'd have to multiply by 3. And that would tell you how far away it is and what is our units of distance. We're giving it in meters. You're at a concert hall, you yell up to the ceiling. It takes 1 second for your echo to go up to the ceiling and back down to you. So how high is the ceiling? So we want to know this height. Well, if it goes all the way up to the ceiling and back to you in 1 second, and we know that in 1 second, sound travels 340 meters. Well, we don't want that full second because the full second says it goes to the ceiling and then back down to us. And it goes 340 meters. Well, we only want the ceiling, so cut that in half. And that would be 170 meters. So the sound must have taken just half as much time to get up there. So half of the speed of sound is 170. And so 170 meters would be your answer there. And give me your best doodle over here. You can draw a speaker if you want. We had the speaker the other day and showing how as it emits sound, those sound waves are going to be spreading out, and you can really do any sort of drawing you want. And yes, the sound goes in both directions and up 360 degrees. But typically the sound or the air molecules in front of the speaker are going to vibrate at higher intensities, so your sound is going to sound better or more audible out in front of your speaker. So you do want to angle your speakers if you can. Some speakers do have actual speakers coming out on all sides of whatever housing the speaker is in, and then yes, you could have the sound going in all directions. But that is the light worksheet there. Awesome job. Let me know if you have other questions, and good luck.